everyone. Let's run through Chem Equilibrium MCQ. Right, we're going to start with the first question, the ACJC Prelim 2018. Okay, they say gaseous dimer Z introduce an empty gas exchange, which has a tightly fitted plunger. Alright, the gas is allowed to expand until equilibrium is reached at a controlled temperature at which 20% of Z dissociates into its monomer W. Alright, okay, for this question, right, so generally what we like to do is this, alright, we have to write the equation first and then we are thinking of doing IC table, alright. Okay, so for this question, right, because the volume is changing, you cannot do the IC table in terms of pressure, alright, because if you want to do an IC table in terms of pressure, alright, the criteria is pressure must be proportional to moles, and that is only possible when is pressure proportional moles, when volume and temperature are constant, right? Then you can use IC table in terms of pressure. But since in this case the volume is changing, you cannot use IC table in terms of pressure. You have to do in terms of moles. All right. So let's see how this is done. Right. So I have X moles, 0. All right. So 20% of it dissociates, right? So minus 0.2x. This is plus 0.4x. All right. So this becomes 0.8x. This becomes 0.4x. All right. So the total number of moles here is actually 1.2x. Okay, the total number of moles is actually 1.2x if you plus them together. All right. This is total moles. Okay, since the plunger doesn't move at equilibrium, we can take it as the inside pressure of the gas is the same as the outside pressure of gas, and we're going to take it to be 1 atm. All right, we're going to take it to 1 atm. So at equilibrium, we can say that the gas inside here is also 1 atm. All right. Okay, so how do you find out Kp? So Kp can be calculated using partial pressure of W square over partial pressure of Z. Okay, partial pressure, we can work it out by doing mole fraction times total pressure. So it's going to be we can actually calculate. All right, this way. Okay, so 0.4x over 1.2x times 1, okay, because it's 1 atm, that's the total pressure. Okay, we're actually applying this formula. Partial pressure for any gas is actually mole fraction times total pressure. That's the formula I'm applying, so times 1, so but never mind, because it is 1, so square over partial pressure of Z, which is mole fraction again, 0.8x, divided by 1.2x, okay, times 1, so just like that. So if you try to solve it, okay, you realize that it will turn out to be, okay, press your calculator and try to solve it. I think the x can cancel out, right? The x can cancel out, all right? So maybe I just try to work it out over here. So this on top here is actually 1/3 square, okay, divided by 2/3. All right. So press your calculator. You realize I think the value should be 0.167. Okay, atm. All right. So actually the answer is B. Okay. The rest of it are wrong. Okay. Let's see why is it wrong. Okay. This reaction involves bond breaking because you are breaking to the monomer. So it involves bond breaking, right? So the forward reaction must be endothermic because it's bond breaking. So this is actually wrong. The pressure inside the exchange at equilibrium will be higher than the atmospheric pressure. No. When the plunger stops moving, the outside pressure must be the same as the inside. So this is actually wrong. The dissociation of dimer X will be favored when the plunger is pushed back into the equilibrium mixture. So when the plunger is pushed back, right? When it pushed back means you're increasing pressure. When increased pressure by LCP, you want to shift to the side with fewer gas molecules to decrease pressure, to decrease the pressure. All right. So which means to decrease. So you should shift to the implied shift left. Okay. So they say dissociation of dimer Z will be favored. This is of course wrong because it's going to shift left. You're going to form more Z. Okay, so let's try a question. So this answer is B anyway. Okay, let's try the next question. Question 2. Phosphorus 5-chloride is a white solid, sublimes at 160. Okay, and this is the equation. Okay, they say the rate constant K applies for the backward reaction and the equilibrium constant Kc applies for the overall process. How will Kb and Kc change, right? How will the values of Kb and Kc change when equilibrium is established at a higher temperature? All right, so when increased temperature, in fact, Kf, so the forward rate will increase, the backward rate will also increase. All right, so increased temperature will always favor the endothermic reaction because you add heat, but LCP, it wants to absorb heat, so favor endothermic. In this case, since the forward, this one is greater than 0, right? So this reaction is endo, so implied position of equilibrium shifts right. Okay, so when it shifts right, imply your Kc would have to increase. So which means Kb will increase and Kc also increases. All right, so which means the answer is A. All right, okay, let's try the next question. Okay, same equation, but now they ask you to calculate the Kc, so maybe I'm just going to write out the equation and we do some calculation. Gas, PCl3 gas plus Cl2 gas. Okay, so I'm going to put ICE. All right, so this is all done in terms of moles. So this is 0.02 moles, right? Vaporized completely in a 2 dm cube container. Okay, this is 0. Right, so the amount of chlorine found at the end was 0.004, so plus 0.004 plus 0.004, and this is minus 0.004. Okay, so over here will be 0.016, 0.004. So if you try to calculate Kc, which is concentration of Cl2, concentration of PCl3 over concentration of PCl5. Alright, so press your calculator. This will be 0.004. You divide by 2 to find out the concentration, square, divide by 0.016, divide by 2. Alright, if you do press your calculator, I believe you should get this value, 5 times 10 to the power minus 4. Alright, so yeah, so if you want to put in the units, it's moles per dm cube. Alright, so the answer will be C. Okay, let's do question 4 now. All right. Okay, the graph shows the change in G, how change in G changes with temperature. All right. So actually, this is actually the equation you can think of, right? There's an equation that's like that. All right. So you're trying to show you that change in G is related to the equilibrium constant. So some things you can take note of. If change in G is less than 0, all right, the K is expected to be much greater than 1. If the change in G is greater than 0, all right, the K is expected to be between 0 to 1, right? So which means actually when change in G is less than 0, right, we learned that the reaction is thermodynamically feasible, feasible. So which means the reaction will actually be very much to the right. Can you see that? It means the reaction can really take place. So that's why K is expected to be very, very, very big, all right? So based on this question, they're asking at which point of the graph will the Kc value be more than 1? It will be more than 1 if change in G is actually less than 0. So check your graph. Okay, whereas this is 0, right? So anything below that, okay, will be Kc will be more than 1. So I will pick these 3 points here. Can you see that? So it has to be 1, 2, and 3. Okay, let's look at question 5. All right. Okay, NOCl is a yellow gas, right? This actually is a yellow gas. Yep, you see this yellow gas. Anyway, can be formed between nitrile chloride and nitric acid, right? Nitric oxide, I mean. Okay, so this shows how the pressure NO2Cl varies with time. So which is actually a reactant, NO2Cl. Okay, what could the changes be made to the system at T1, T2, and T3? All right. Okay, over here, let's take a look. If NO2Cl was removed at T1, the graph will look like this. Okay, we'll actually see a big drop. If NO2Cl was removed, you see a big drop, but you don't see it on the graph. So definitely, I take it as A and D are wrong already. A and D are actually wrong. Okay, if temperature was decreased, this reaction is actually exothermic. So if you decrease temperature, it will favor the exothermic reaction, because when you decrease temperature, the system wants to increase temperature by producing more heat. It will favor the exothermic, and the position of equilibrium will shift to the right, okay, and which means imply concentration or the pressure NO2Cl must actually decrease, okay, actually we have to decrease. All right, so as it shift to right, so actually it's decreasing, okay, it's good. So this actually is possible. All right, so NO2, if NO2 was removed, NO2 you take away, you remove NO2, you decrease it. So by LCP, equilibrium wants to shift to right, so NO2Cl will also decrease. So this is actually feasible. So okay, I put them, both of them are feasible. Okay, let's look at T2. Okay, T2, you can see the graph goes up like that. I'll say this is wrong already. All right, why? NO2Cl was added, the graph will have to show it's like going up. There must be a line that goes up. Okay, it was added. Okay, but you don't see that line, means this is wrong. Okay, so which means which means actually that leads us to only one answer, which is C. Okay, but let's run through the whole of entire C. Okay, temperature was increased. When increased temperature, it will favor endo. All right, so favor endo means your position equilibrium will shift left. Okay, favor the endo, right, shift left. Okay, so pressure of NO2Cl will actually increase. So it does go up over here. So this is correct. Okay, over here you can see there's a bump up. So this was added, which is true. Okay, so yeah, so the answer should be C. Okay, let's move on. Okay, let's look at this question. They show you two graphs, and they say the number moles of L. They say what's the correct identity of L and the correct magnitude of the pressure. Okay, so very quickly, when there's an increase in temperature, right, there's an increase in temperature, you notice that the L actually decreases, right? The amount of L actually decreases. Okay, so increase in temperature will always favor adding heat. The system will absorb heat, favor endothermic. All right, and this reaction is actually exothermic, as you can see. It is actually exothermic, it's negative. All right, so which means position of equilibrium shifts left. Okay, actually it shifts left because favor endothermic. So since L is decreasing, all right, L is decreasing, it means that L must be a product. Okay, product, because if it shift left, then if it shifts left, right, then the concentration of the product will decrease. Okay, so I'm going to say that L is actually SO3. Okay, let's look at the next question. What happens when I change pressure? Okay, for the other criteria, we're going to just keep temperature the same, and we're going to change the pressure. Okay, let's see. So over here, take it as the temperature is constant. Okay, so increase pressure by LCP. Okay, it will want to decrease the pressure, right? So it must shift to side with fewer gas molecules, right? So where will it shift to? Imply equilibrium, position of equilibrium shifts right. Okay, shifts right. All right. Okay, so increased pressure shifts right. Okay, increased pressure shift right. So shift right actually means you produce more SO3. Okay, shift right means produce more SO3. So in that case, since SO3 is higher here compared to here, right? So which means from P2 to P1, you are actually increasing the pressure. You're actually increasing the pressure because we increase pressure. Shifts right, so you produce more SO3. So when you increase pressure, there'll be more SO3 because SO3 from here move up to here. Okay, so which means P1 must be greater than P2. All right, which means the answer is C. All right, let's look at question 7. Okay, let's look at question 7. HBr gas was decomposed in a sealed container at temperature T. The decomposition equation is shown below. All right, which of it is false? Equal amounts of H2 and Br2 are formed at equilibrium. That is definitely true. All right, because their ratio is 1:1. When the catalyst added, the rates of the forward and reverse reactions are increased by the same extent. That is definitely true also, right? The rate of forward and the rate of back increase by the same extent. Kc will decrease if the reaction is carried out at higher temperature. So you increase temperature, it will favor the endo because it wants to absorb heat. So position of equilibrium will shifts right, because since the forward is actually endo, right? So it shifts right, imply your Kc will increase, okay, because you have more products than reactants at equilibrium. But here they say Kc will decrease, so this is actually false. All right, false. So that's why the answer is C. The question is asking for which is false. So when the volume of is decreased, right, means you're increasing pressure. All right, you're actually increasing pressure. So when increased pressure, it wants to shift to the side with fewer gas molecules, but the fact that both sides has 2 moles of gas, so it will be unaffected. All right, so actually it's true. Okay, let's move on. Okay, let's look at question 8. Okay, so for this question, let's see how it goes. When I increase pressure, let's look at the products. So when I increase pressure, as you can see, the percentage of products, right? Products actually decreases. Okay, so which means, but when I increase pressure by LCP, it wants to shift to side with fewer gas. All right, so if the shift to side fewer gas, so can you see that the percentage of product decreases, which means it's actually shifts what, to the left. You see that shift left, that's why the number of products is actually decreasing. Can you see that the products is decreasing? So shifting left is the side with fewer gas molecules. So let's check. So I guess the left hand side must have fewer gas molecules. I think this one should be a gas here. I think there's something missing over here. So definitely A is correct. Okay, possible, not really correct, but possible. This one has 2 moles of gas each, so this is wrong. The left hand side must have fewer gas, right? This is 1 mole of gas and here got 2 moles of gas. So this is a possible answer. This one has 4 moles of gas and this one 2 moles of gas. So this is definitely wrong. Okay, D is definitely out. Okay, so we'll choose between A and C. Okay, let's look at the next part. Okay, now we're going to look at change in temperature. So from here to here, when I increase temperature, it will always favor the endothermic reaction. Okay, and you can see that amount of product is actually decreased. All right, so which imply that equilibrium also shifted to the shifts left because the amount of product actually decreased, right? So left is endo, so backward reaction is endo, imply forward reaction is exo. Alright, so I'm going to choose one that's exo, and this is one that's exo. That's why the answer should be C. Alright. Okay, let's look at number 9. Alright, L plus M give you Q and R. Okay. Which of the following information cannot be deduced from the graph? Okay. If you look at this question, you actually know. Okay, I'm just going to write this down first. L plus M give you Q and R. Okay, and you have 1 mole of this 1. Okay, this is moles. ICE. All right, ICE. So they told you the R was present at intervals where the experiment was repeated at the same pressure but at 700. Okay, it means there are 2 graphs here. All right. Okay. You can see that, say I use the first experiment. Let's say I use the first experiment, experiment 1. I call this experiment 2. You know that the final amount of R is actually 0.7. Okay, so I put 0.7 plus 0.7 plus 0.7 minus plus 0.7 minus 0.7 minus 0.7. So you can see that I have all the equilibrium values. If I have all the equilibrium values, right, I can actually calculate the Kp. All right, I have all the equilibrium values. I can calculate the Kp, all right, quite easily. Okay, why is that so? because the question said it reacted at constant pressure. So pressure didn't change. So you can use you can do this. You can find the partial pressure of L at equilibrium, which is actually 0.3, the number of moles, over the total moles, which is 2. Add up together, everything is 2. So over 2 times the pressure that you know, a constant pressure, right? So you can get this value. You can find the value, you can find the partial pressure for all the gases. Definitely you can find the Kp, right? This one is true. This one, so I say which one cannot, right? I say this one can be determined. The forward reaction is exothermic. How do you know the forward reaction is exothermic? So let's see. When you increase temperature, you can see when you increase temperature 350 to 700, the percentage or the amount of R actually decreases. Okay, actually decreases. So if R decreases, means the position of equilibrium actually shifts left. Okay, that's why the R actually dropped. Okay, see that? So increased temperature will favor endo. So going backwards is endo, forward is exo. So forward reaction is endo, exothermic. Yes, you can actually determine. Yep. The activation energy of the forward reaction is high. In fact, there's nothing mentioned about activation energy. This is the one that you cannot deduce. Alright. Equilibrium is achieved at a faster rate at high temperature. Yes, because of higher temperature always result in a faster rate of reaction. Yeah, so this one is definitely true. Can. Alright, so the answer is C. Okay, let's look at question 10. So this is the Haber process. Alright. Okay, average change at time t would result in a graph shown. Okay, you notice there's a spike for all of them. Everything goes up. So how does the concentration of everything go up? Alright, so what you can do is you can actually decrease the volume. Yeah, once you decrease the volume, because concentration is most of the volume, so if you decrease the volume, the concentration will increase, and it will increase for all the gases in there. So this one should be just C straight away. Alright, I can see it immediately. Okay, let's look at question 11. Okay, this expression for sulfur dioxide plus oxygen give you SO3. You have the Kc. I'm going to write down the Kc first. Alright, the Kc will be SO3 square, SO2 square, O2. Alright, so this Kc here is actually, I'm going to call it Kc prime. Yeah, it's actually slightly different. It's SO3 square over SO2 over O2 to the power half. So you can see that this Kc prime is the square root of the Kc here, right? Okay, so let's see, I'm going to put IC table in terms of moles, ICE. Alright, so this one will be 0.5, 1, and okay, so 0. Okay, so equilibrium, this is 0.3, so this must be plus 0.3 minus 0.15, this will be minus 0.3, 0.2, and 0.85, right? Okay, so then you can actually calculate your Kc, right? Kc is equals to, you have to divide by the volume. Okay, so 0.3 divided by 0.5, right? And then you square it over SO2 is 0.2 divided by 0.5, you square it, and 0.85, right, divide by 0.5. Okay, this one you don't have to square. Okay, if you do your calculation, I believe you should get 1.3235. Alright, so now you're gonna calculate the Kc for this one. Alright, for this one, in fact, I'll call it like Kc prime in that case. Okay, Kc prime, that's the one that you want to find out. Okay, so this is equals to square root, okay, 1.3235. You'll get 1.15, right? So the answer is B. Okay, let's look at the next question. 12. Which statement about the effect of adding a catalyst to a reversible reaction is correct? So adding a catalyst, it increases the yield of a product. That is false. Increases the rate constant for the forward reaction. Yes, that is true. Alright. Increases the equilibrium constant. No, equilibrium constant is only affected by temperature. So this is false. Increases the activation energy of the reverse reaction. So in fact, it should decrease. This is not increase. So this is definitely wrong. So false. So the answer is B. Right. Let's look at question 13. So look at this equation, and they say they give you the forward and backward rate constants. All right, K1 and K minus 1. What happens if the temperature is increased? All right. So if it increased temperature, it will actually favor the endothermic. So this reaction is actually exo, right? This reaction is actually exo. So favor endo means position of equilibrium will shift left. Shifts left, right? So in this case, the Kc will actually decrease, right? Kc will actually decrease. Okay, but when you increase temperature, what happens is this. When you increase temperature, the forward reaction will increase, the rate constant, and the backward rate constant will also increase. But since equilibrium shift backwards, so which means the increase in the backward rate constant is greater than the increase in the forward rate constant. All right, yeah, but at the end of the day, increased temperature, both will actually increase. So the answer is D. Okay, let's look at the next one, question 14. Okay, look at this is a reaction between carbon monoxide, chlorine, and COCl2. What conclusion can be deduced from the graph is incorrect. They want incorrect. The rate of the forward reaction equals the rate of the backward reaction at 7 minutes. Okay, at 7 minutes is over here. So actually 7 minutes is actually at equilibrium. So this is correct. Okay, because it's at equilibrium, this is correct. The change in concentration from 7.5 to 10 was produced by increase in volume at constant temperature. Okay, the change in concentration was produced by increase in volume. Okay, the thing is, you can see that the concentration all went up. You can see that all the concentration actually went up. So if concentration went up, means the volume must decrease, not increase, right? So this is definitely wrong. Okay, it should be decrease, not increase. So this is incorrect. Alright, so I think the answer is already B. The equilibrium constant may determine at 7 minutes is 0.417. So can you tell, right? Let's try to do a bit of calculation here. Kc equals to COCl2 over COCl2, can? So these are all in concentration. COCl2, the value is 0.2. Okay, CO, the value is 0.8. You see, 0.8. And for Cl2, the value is 0.6. Okay, if you pass your calculator, I believe you should get 0.417. Right, you pass calculator, you should get 0.417. Okay, so this actually is correct. Okay, the change in concentration for 10 to 15 minutes was produced by the addition of more chlorine. So look at the 10 minute. Okay, yeah. So at the 10 minute, you notice there's actually a bump up here, right? So actually there's an increase in chlorine. So this is actually correct. Okay, so that's why the answer is B. All right. Okay, let's move on to the next question. Question 15. Carbon monoxide burns readily in oxygen to form carbon dioxide. So the equation should look something like this. So this is combustion. Combustion is an exothermic reaction. Anyway, they told you is it happens readily. Yeah. So I guess normally it should be exothermic. So the +4 oxidation state of carbon is more stable. That's true. Carbon dioxide actually, the +4 is actually more stable than the +2. This is +4. This is +2. Okay, so this one I think it is correct. Because it happens more readily, right? Yeah, so this is CO2 is energetically more stable, lower energy level. The standard enthalpy of formation of carbon dioxide is less negative than that of carbon monoxide. Okay, so how does it work? Okay, so if I have this energy, right? This energy, right? So I will start from carbon plus oxygen, right? So plus O2. So if I'm going to form carbon monoxide, right, is over here, all right? Then only half oxygen will be used, the other half O2 will not be used. You see that? But this can continue. This is negative, right? So from here to here, you can see this is negative. Negative, yeah, exothermic. This is a negative value. So I can draw one line. This become carbon dioxide gas. So I'm going to just draw it out here. So you can see that this is actually enthalpy of formation of carbon dioxide, and over here is enthalpy of formation of carbon monoxide. Okay, so the enthalpy of formation of carbon dioxide is less negative. Not true. It is more negative compared to this, right? So this is definitely wrong. Okay, this is wrong. Okay, the value of the equilibrium constant for the following reaction is likely to be high. Definitely, because you're going to form carbon dioxide very easily. Okay, you're going to form carbon dioxide easily. Okay, carbon dioxide is more stable. I expect the Kc to be a high value because equilibrium is more towards the right. So I think this is true. Okay, and so I believe the answer should be C. Okay, the answer this should be C. Okay, let's move on to the next question. Okay, PQ and PQ3 start to reach equilibrium, and they gave you the moles, right? Maybe I'm going to write this down all again. Okay, you start with Q, you started with 0.5. I will put down 0.5. I'm doing moles again. All right, moles. Okay, P, they say the initial moles of P was 0.2. PQ3 initially was actually 0.4. Can you see that? All right. So at equilibrium Q is 0.2. And at equilibrium PQ3 is 0.5. Can you see that? So this actually from here is plus 0.1, and this is minus 0.3. Everything makes sense. This should be minus 0.1. So this should be 0.1 over here. All right. So after that, you can calculate the Kc. You just punch into your calculator. Concentration of PQ3, concentration of P, concentration of QQ. Right. So this will be 0.5 divided by 5. Right, because the volume is 5. Right. This is 0.1 divided by 5. Here will be 0.2 divided by 5, and don't forget to cube it. Right. Press your calculator, or you actually don't have to press your calculator, you do some simplification, right? Let me see, can you simplify? Yeah, I think I can see that this is becomes 0.5, this is 0.1, this is 0.2 cube. I guess I can cancel this 5 and the 5, it still has the 5 cube over here, right? So I have to bring it up, 5 cube. Alright, so which means this look like answer is C. It's okay? Okay, let's run through the next question. Okay, 17. Which statement is correct about a reaction for the equilibrium constant is independent of temperature? Okay, equilibrium constant is independent of temperature. So for equilibrium constant, normally the Kc will change when temperature changes, but the only time that is independent, right, is when change in H is 0. Alright, when it's 0, that means there's no bias to shift right or shift left. Okay, let's look at the first option. Okay, rate constant K, actually there's a formula like this, EA over RT. Yep, this EA is of course activation energy, and this is temperature. So if the temperature changes, the rate constant will change. Alright, so rate constant for the forward and reverse are both independent. That is not true. Temperature changes, rate constant will change. So this is false. I put false. Temperature has no effect on the position equilibrium. Yep. So for this case, since this reaction is neither exo or endo, when you increase temperature, there is no bias. It won't shift more to right or more to the left. Okay, so has no effect. This is definitely true. The forward and reverse reactions have equal activation energy. So how do you draw a graph that is energy profile that change H is 0? So if that's the case, right, energy, and I call this progress of reaction. Progress of reaction. So for enthalpy change is 0, it looks like that. Okay, so there's no enthalpy. So the forward activation energy and the backward activation energy are actually the same. Okay, so for have equal activation energy, that is true. Okay, we put on true here. Okay, next one. The entropy change is 0. Entropy change, you can't tell from this part here, right? So I don't think you can tell anything about entropy change based on this. So I put false. Yeah. Okay, so this means that answer must be 2 and 3. Okay, 2 and 3. Okay, let's move on to question 18. Okay, when Q is allowed to react with R2 in a molar ratio of 2:1, the initial total pressure is actually 3 atm. So which means I can say that Q2 is actually 2 atm. So we'll do it in terms of atm already. Yeah? So this is 2 atm, and this R2, we can take it to be 1 atm. All right. Okay, this one I'm just going to put 0. Okay, 20% of the equilibrium mixture is found to be Q2R. So I'm going to put down minus 2x minus x plus 2x. Okay, so it's 2 minus 2x, 1 minus x, this is 2x. All right. They say 20% of the equilibrium mixture is found to be this. So I'm just going to sum up everything here. Sum up everything here will be 3 minus x. All right, 3 minus x. So which means 20% means 0.2, right? It's actually 2x over 3 minus x, right? Out of 2x out of the total. Okay, and that's 20%. So if you work it out, okay, let's work it out nicely. So maybe I take it as this. I know this is actually 1/5, right? So 3 minus x is equals to 10x. So x is actually equals to 3 over 11. All right. Okay, so with that, you can actually sub back the x into the E, all right, to find the equilibrium partial pressure. All right. So let me just work it out nicely over here. So Kp is equals to pressure of Q2R square, pressure of Q2 square, pressure of R2. Okay. So this one, 3 minus 3 over 11. Oh, sorry, not 3 minus this, but 2x, right? So 2x is 6 over 11. Okay, so 6 over 11 square over 16 over 11 square, 1 minus 3, so it is like 8 over 11. Okay, and you can press your calculator, and if you do it nicely, you'll see that the final answer will be 0.194. Okay, atm minus 1. Alright, so that's how it's done. Answer is C. Okay, let's look at the next question, 19. Okay, so over here, this based on this, there's aqueous and gas. So I'm going to use Kp. Alright, Kp is equals to partial pressure of Z over partial pressure of Y. Alright. Okay. They say which of the disturbance at time t can account for the observed change in the graph above. So an increase in pressure, okay, when there's increase in pressure, in fact, since both sides has equal number of moles of gas, equilibrium will not shift. So, but this shows a shift, right? Which means this is wrong. Okay, because increase in pressure, there is no position of equilibrium does not shift. No shift in position of equilibrium. All right. Addition of water into the aqueous solution, as you can see, Kp is only dependent on pressure of the gases. So adding water into the aqueous solution, it also does not affect position of equilibrium. Okay, because position of equilibrium is only affected by the pressure of Z and Y. All right. Increase in temperature. So increase in temperature, you'll notice that it will favor the endothermic. So favor endothermic. This is actually exo. So position of equilibrium shifts left. Is okay. So a shift left means you have more Y. More X shift left. So shift left, more Y and less Z. Right. So more Y. Okay, but you should notice Y is actually coming down. So that's why this is also wrong. Right. So which means answer is none of the above. Okay, none of the above. All right. Okay, let's look at the last question, question 20. Okay, this one you need to do a bit of calculation. Okay, let me just write it up first. Okay, and I'm putting all the values that's needed. Okay, they say at equilibrium 30% had dissociated, so I'll let this one be X. Okay, the total pressure according to 30% of the gas dissociated according to the equilibrium, and the total pressure was PATM. So PATM is actually the total pressure at the end. And since this is a fixed volume and fixed temperature, I can use in terms of ATM. Okay, I can do in terms of pressure, right? Because if PV equals to nRT, pressure is proportional moles because volume and temperature are constant. All right. So if that's the case, I can use IC table in terms of ATM. All right. So that's a criteria. So this is X00. 30% dissociated is minus 0.3x. This will be plus 0.3x, and this is half of it, 0.15x. So this is 0.7x, 0.3x, 0.15x. Okay, you add them all up, this is equals to P. All right, so I'll say, work it out. Let me check. 1.15x is actually equals to P. All right. Okay, so let's calculate a Kp now. All right, Kp is equals to pressure of Cl2, pressure of NO square, pressure of NOCl square. Okay, can I put in the values? I'm just gonna put in 0.3x square, 0.15x over 0.7x square. All right. So work it out, it should be 0.3 square times 0.15x over 0.7 square. Okay, and after that, sub the x. From here, x actually equals to P over 1.15, right? So sub this value inside here and work it out. I believe you should get 0.024 P. Right, so this answer is B. Right, so that's how we do the questions for chemical equilibrium.
Thank you for watching the Twig Learning Center chemistry tutorial. I hope you learned something new. Don't forget to click the subscribe button so you'll be updated when new videos are posted.